You are explorers. It's who you are. You think bigger and smaller. You think faster and slower. You take inspiration from everywhere so you can innovate more. Your visions start in rooms, move to desktops, then to pockets, then to wrists. You ask big questions, pose impossible challenges, all the while seeking those who believe like you do. At Keysight, we believe. We nurture the far-fetched, remove barriers that limit possibilities, and stay ahead of the standards. We redefine precision in measurement so you can go smaller. We integrate and expand test functions so you can streamline complex workflows. And we surface intelligent analytics so you can innovate faster. We believe in you. We are Keysight. We accelerate innovation.
Today we will hear 9 presentations. These presentations were chosen by the preliminary assessment of the works, and we are going to estimate our finalists by the following positions. It is relativity, relevance of the problem solved in work, practical significance of the work, scientific novelty, state of the art, and the evaluation of the partnership, the likelihood of investing in the project. This is the list of assessment that I asked Roman Gorbunov to give this list to each of our dear experts. Time requirement for the participant. This time requirement will be checked very strictly by my side, very strictly. Please, no more than 7 minutes to your speech. And next 2 or 3 constructive questions. Okay? Thank you. Our first finalist, Vadim Sidorov, Tallinn University of Technology, with the work Topology Morphing Control with Soft Transients for Multimode Series Resonant DC-DC Converter.
Good evening, dear colleagues. I'm the second year PhD student of Tallinn University of Technology. And today I would like to...
Please speak to the microphone.
Okay. And today I would like to present you topology morphing control. Now, DC microgrids are becoming increasingly popular because now many portable devices in a residential building already can be connected to DC. For example, chargers for phone, for laptop, LED lighting. Also, I see home appliances with internal inverters. And DC microgrids consist of centralized DC bus voltage of 350 volts, centralized interface inverter for connection to the utility grid, distributed various energy source and storage, which require front-end DC-DC converter. In this study, I focused on this converter. That should be step-up converter, bidirectional, and provide wide input voltage range, galvanic isolation, high efficiency. According to these requirements, we decide to utilize series resonant DC-DC converter with fixed switching frequency. The wide input voltage range is required for operation with PV under partial shading condition, because when something covers the PV panels, for example, leaves or dirty, the global maximum power points is placed in different voltage. And our analysis of majority used PV panels and batteries shows that the front-end DC-DC converter should have input voltage range from 8 up to 6 volts. And the Series C converter consists of input side and output side switching cells and a resonant tank formed based on series capacitors and isolation transformer. The series capacitors allows for reconfiguration full bridge cells into half bridge. Thus, the voltage gain can be changed from 1 to 0.5 or from 1 to 2. And thus, the input voltage range can be extended. This is main idea of my study and called topology morphing control. At the same time, buck and boost control methods can be applied for controlling input voltage. In total, the Series C converter operates under 6 control modes, and input voltage range can be significantly extended. The prototype of the converter was built to verify operation in different mode and transition between them. The input voltage range of our prototype equals from 10 to 75 volts. It covers required input voltage range and also will allow operate with the next generation of PV panels. The power of the converter equals 300 watts. And my experimental analysis shows that the efficiency of the converter is below 90% in each input voltage range in 2 directions, I mean in forward and backward direction. And the maximum efficiency of the converter equals 97.2%. This slide shows one of the example of operation with some PV panels. It is 72 tails PV panels. This figure shows that our control system can scanning PV and switch between different topology without any high oscillation in input voltage and current. And control system can find maximum power point for 60 milliseconds. That's it. Really small time. And in conclusion, I would like to highlight that we built simple topology with fixable controlling that consists of only 8 control switches, and only 2 of them has hard switching. And converter operates in wide input voltage range from 10 to 65 volts with efficiency 97.2%. It should be highlighted that this work is a project with Estonian Ubik Solution Company and founded by Estonian Development Fund. My future research will focus on application-oriented study and designed efficiency transformer and designed control system for operation with battery. So during this work, I published different journal papers and conference papers that you can find in my Google Scholar account or Kit accounts. And that's all from my side. Thank you for your attention.
Thank you. I think it was a very interesting work, and thank you for respect our time requirement. Perfect. And first question from me: what your own contribution in this work?
My own contribution, I designed a control system for this topology, for reconfiguration topology from half bridge to full bridge. I measured experimental efficiency. I carry out different experiments with PV. I designed control system for operation with PV and find the global power point. And also I will design control system for operation with battery and PV panels and figure out what is its power source will be connected to our converter.
A lot of?
Yeah, of course, it is my main project during my PhD study.
Okay, now a question. Do you have prototype and how many example? How many example of prototype do you have? First question. And second question, you see this very, very common things. And please give comparison with a commercial example which have efficiency, power, trend, and so on. Table, where is it?
Okay, the first answer. Right now we have, this is the first our prototype. Now we designed with UBI company new first industrial prototype. In case of comparison, I figure out different industrial prototype and figure.
Show table.
I can draw. Okay. Must have. Where's the requirement for it? Is if must have?
You must have, because when I choose it, I will compare parameters of your prototype.
Okay.
Commercial.
When we finish our industrial prototype, we will show table on our website.
Yes, but this is disadvantage of your presentation, and very common disadvantage. You see, in future, every time.
I can promise you that all industrial prototype has small input voltage range from 20 up to 35 volts. Our prototype.
What about size, weight, efficiency, and so on? Whereas many.
Of course, it is developing. It's not final industrial prototype.
Okay, very interesting discussion. And another question, please. Thank you, Vadim.
Thank you for your attention and for your questions.
And now we're going to our next finalist, Daria Lipchak, with its work, Sensorex, the challenges of engineering implementation of low-cost, non-invasive pulse oximeter applicable to diverse patient population.
Hello, ladies and gentlemen. My name is Daria Lipchak, as you heard, and I am software engineer at the Research and Development Department of my company. So today I would like to present you the results of our team work provided the last quarter of the 2020. So first of all is the low-cost pulse oximeter demanded by market and why. Indeed, the demand on pulse oximeters is increased last year because of the pandemic, because it became a decisive factor for diagnosis of COVID. So we see there are a lot of devices on the market, and to overcome the challenge, we need to lower price as far as possible. So when we study the patents already available on Google, there are a lot have been done in the industry, starting from the physics of the sensor, which is traditionally just two wavelengths, light emitting diode and a photodetector, and continue with the post-processing technique, which nowadays is the most wanted feature, because the difference between the amateur pulse oximeter you can find for about 600 rubles and the professional one is accuracy and compliance to the standards. And to meet the standards, you need to apply a very sophisticated technique to filter, to extract their pulse and saturation from the signal. So when we gather all the requirements from the standards and from our stakeholders, we analyze them, and the price also, we found that they are contradictory. And we need to choose a very reliable architecture. So I would like to highlight the three key features of our device which we implement and which are key difference from the current existent devices. First of all, because of the low price and the size of measurement board should be limited, we need to implement more software filters than hardware ones. Secondly, we need to think about amplification, and then we choose to do our device based on STM32 microcontroller which has embedded gain control, which will give us more space for our PCB board. So then realized that there are a lot of interferences, and we need to choose the proper discretization frequency of the signal, and we need to think about subtracting of the ambient light, the background. So the first step of the first group of the challenges is connected with primary extracting the signal. So I think everybody knows that pulse oximeter is operating with two wavelengths, two LEDs, which should be turned on and turned off consequently. But what we did, we are not only turning it on and turning it off, we are forming the impulse. Then we can adjust it easily by the software and vary our calculation complexity. Then we also add a little hardware filtering and make this gain control by the STM32. The second challenge is software filtering, because the controller we use have only 32 kilobytes of RAM, and this finite impulse response filters are very consumptive. So we made some techniques. We pre-generated the constants for the filters we previously modulated in MATLAB. Then after the signal goes to the low pass filter, it will become available for monitoring for plethysmogram, but it is not enough filter rate for further Fourier transform. I'm sorry, is it something wrong? For the further Fourier transform is for pulse extraction. So we also need the bandpass filters shown on the downside. And after that, we need a special lattice filter, which indeed is adaptive noise canceller, which help us to provide the correct saturation extraction. And this technique is very close to the Massimo technique. And Massimo is a well-known and very respectable developer and manufacturer of the pulse oximeter. And for neonatology, which is our priority for devices, it is, I think, the most desirable trademark of pulse oximeter to be embedded in the device. So we did a lot of optimization for memory. And the third we realized that, okay, I'm sorry. We implemented the algorithm to adjust our intensity, aiming to adjust the intensity for different patients, for example, neonates or patients of different gender or obese, for example, patients, different morphology. So it results in a system which is easily connected to the personal computer and already worked in neonatal intensive care unit. And it is a good opportunity for us to collect data because we have embedded memory storage, and further we can use it for further investigation in the field of perfusion variability index or pulse variability, which is very perspective. This board we developed for the measurement is also now produced as an OEM module. So it can be used in various devices and it can be developed with the help of science. So thank you very much.
Thank you. I think 1 second left. And I wanted to ask my first question. So you are the industry partner, right? Yeah. And do you have any academia partner in this work?
Indeed, this is the problem, and this is the reason why I am here today, because I have only a master's degree and I tried everything myself. And probably I need some scientific help in future.
Thank you. Question, please.
Konstantin Tafintsov, Huawei. So my question is, can you help me to realize what is the new idea here implemented, or you just try to reproduce some existing ideas and create just a good device?
The science here first was in optimization, and its unique solution realized on the very cheap STM controllers without not many analog circuits. The second, when we implemented the ideas from the patents we were based on, we enhanced it indeed. So now we validated with the Massima. We have our device, and we have Massima Red 57, I suppose, also a handheld pulse oximeter. We put it together, and I think ours is best, is better. And it's already registered on the Russian market as a safety and effective device, medical device for professional use.
Maybe you can give some specific, simple detail, like you just applied the FIR filter here and nobody else applied it, or you choose specific shape of the impulse response or whatever. Any such specific scientific?
I understand your concern. I could say that, but it would not be true because filters are very common. But the unique is the part which is going after the filters. When we extract saturation, this adaptive noise canceller, it is modified for our needs, for our patients, and this is novelty.
Got it. Thank you very much.
Please clarify your personal contribution in this work.
I am a leading software engineer who create the embedded software for this measurement board.
Okay.
We have 2 software developers and 1 electronics designer and 1 mechanical designer on this project, and we did it for less than a year, like 4 of us. Not 25. We have 2 software engineers, 1 electronic designer, 1 mechanical designer. That's all our team.
Okay.
Okay. I understand. So if you see the block scheme, there are 2 boards in their device. I did the measurement board. My colleague software engineer did the indication board, if you speak about embedded software. The electronics was designed by electronics engineer. The housing was designed by mechanical engineer. That's all. No, STM32 controller.
Thank you very much.
Last question, please. And,
Please.
so, I mean, we know that, as you said, at now moment, Massima and Nelcore company has high accuracy of measurement. But if you compare, I mean, Nelcore and Massima, what will be your results? I mean, what is the difference? Did you measure it?
The key feature is the motion resistance for Massima. Why everybody loves Massima? Because you can tap with the fingertip and nothing happens with saturation. It is not the old measurement, it's really the good filtering. So we did the same.
Thank you for your report. Please answer this one question. How do you deal with movements artifacts?
Yeah,
Thank you.
It's very interesting question. First of all, we do this discrete saturation transform like Massima. So we have a distribution of probability of saturation being in the signal in the whole range of saturation, like about from 30% to 100%, and the most the variance of the saturation, which is the most probably is in signal, is search from the right to the left from 100. So it's arterial saturation, no matter. But we also calculate the width of the peak of this distribution. And when there is a lot of movement, we can control it, and we can take off these periods of time. Like, this is incorrect period with movement, we will not calculate saturation here, and wait for the correct snapshot will come.
Daria, thank you. Please, as I understand, do you have a prototype of your device?
Yes.
Maybe do you show us?
Yes, of course.
Okay, please. Okay.
We have a lot of work to do because it can be slower, like about 25 seconds for sometimes to get the proper snapshot when you measure the patient. So.
Okay, I think Daria can give, if she can give this prototype to our dear audience. I understand that it is very actual topic. Thank you very much for your work. And we have to move on. Our next finalist, Viktor Chechetkin. Viktor Chechetkin. Comparison of the Coplanar waveguide to microstrip line transition design in the 77 GHz frequency range. And excuse me, dear experts.
We can come back later.
Yes.
Please be quiet. Sit down, please.
We need to respect our speaker. That is why I think you can move your discussion.
Okay.
Please.
Good evening, dear colleagues. As I was introduced, my name is Viktor Chechetkin, and currently we are working on the device, which is an automotive radar in the 77 GHz frequency range. It will be used as a part of the intelligent driver assistance system, automatic control systems for unmanned vehicles, and also as the intelligent farming systems. This radar is now the state of the art because there are currently two frequency ranges for these radars. One of them is 24 GHz and another is 77 GHz, which is allowed in many countries nowadays. Okay, first of all, you can see here the outline of my presentation. I will skip it. First of all, we found some references, some reference designs. Here, depicted number 1, you can see the demo board from the Texas Instruments, and you can see that from this IC, from this radar, there are CPV lines, so Coplanar waveguide grounded lines, which do have a transition to the microstrip line, as the microstrip antennas are usually fed up by the microstrip lines. The second one is the radar from the NXP. It is also a demo board, and the third one is the most interesting. It is one of the two most spread around the world radars. It is from the company called Continental. It is the Continental ARS-4 radar. Another company that produces a lot of such radars is Bosch. And you can see that there is a lot of solder over here. This is because there was a shielding, a metal shielding from the electromagnetic influence difference, and I will come to this a little bit later. Also, you can see over here that this is another demo board, and also the IC is covered with the shield, also to pass the EMC tests. Okay, first of all, we took the reference from the Texas Instruments. This is from their datasheet on the IC. And you can see that here is just a simple transition from the CPV line to the microstrip line. There are some wires over here. And well, this is rather simple, and first of all, we tried to make something the same, but which wouldn't be the same as the reference design, because we did have such configuration of the MIMO antennas that the distance between them, it is depicted by the letter D over here, is only 1.9 millimeters, so they are separated by only half the wavelength, and so they are very close to each other. So you can see here in the table all of the parameters of this direct transition design, we called it so. Here are the S parameters from the electromagnetic software. The S21 is only minus 0.34 decibel, and the return loss parameters are less than 20 decibel. But then our directors, they think about that we will need a shielding, and you can't use the shielding when you do have a direct transition design. So we needed to find some other way to make the shield and to make the transition. So first of all, we started to think about the reference designs for the substrate integrated waveguide transition, and we found that we can make the transition only with a simple taper over here, and this was rather fine for the microstrip line. But there was a problem with the CPV line, as this transition is rather hard to implement, and we found only a couple of references when people made the line from the CPV to the substrate integrated waveguide. So we made our own design where we do have the taper to come to the microstrip line, we do have this structure to come to the CPV waveguide line, and you can see that here we do have a substrate integrated waveguide, and on this place the shield will be soldered. So we can protect our IC from the electromagnetic emissions. Here also are the S parameters of the transition. But as we are all working with different manufacturers, the manufacturers said us that they don't have an opportunity to put the wires so close to each other as we wanted to do. So they were able only to put the wires on the distance of 0.4 millimeters, 0.45 millimeters between them. And we found out that we can't do the substrate integrated waveguide that we wanted to. We needed to check if we will have the decoupling coefficient as we wanted to have for the MIMO radar. As you can see over here, here are the parameters for the wires distance of 0.3 millimeters, and they all are less than minus 36 dB. And here are the S parameters showing the coupling between all the ports when the distance between the wires is 0.45 decibel, 0.45 millimeters, and you can see that in some cases the decoupling coefficient is 11 decibels higher than we wanted to. On the whole, we produced this design, and it showed that there are no problems. You can see a part of the PCB that we designed over here. Here is the taper from the microstrip line to the substrate integrated waveguide, and from the substrate integrated waveguide to the CPV line. We couldn't make the experiment because there is an IC on one side of the line, and there is antenna on the other side of the line, but the test that we made with the radar showed that it works as we wanted to. Thank you for your attention.
Thank you, Victor. I think it was perfect timing. Question, please. Oh, okay, please.
Why haven't you used
Microphone, please.
Stand up.
Please. Why haven't you used another PCB manufacturing company to maybe another company can help you with distance between wires?
We couldn't have found a company in Russia which can produce such PCBs on these materials. This is Rogers 3003, and it is very thin, 0.127 millimeters. And they didn't have technology to put the wires on such distance between them.
Okay, and what about maybe foreign manufacturers like Chinese?
Yes, so we ordered the PCB from our Chinese partners.
Could you repeat, please? I wasn't interrupted.
So on the whole, we managed to produce the PCB with our Chinese partners.
Oh, I see. Thanks.
Question, please? Please.
As I know, Texas Instruments produce ASIC for 77 gigahertz mobile radar navigation, and PCB the same. What is the new and better one? This solution, and much more in data sheet there is structure and everything.
Yeah, we did have some requirements for the radar. For example, the distance for the detection is 250 meters. So we needed to design our own antennas for the long-range radar and our own antennas for the short-range radar, because the ones that do have the Texas Instruments.
Is it better than in Texas? Your antenna is better than Texas.
On the whole, this radar do have the same or better characteristics than the radars that are commercially available.
Konstantin, please.
This is Konstantin speaking again from Huawei, and I have the same question. Please help us to realize what is the new idea here. What is the scientific new ideas?
Okay. Well, the thing is that in available demo boards or in the commercially available radars, there is no such structure when you do have the CPV line coming from the IC, and you do have the microstrip line coming to the antenna, and you do have shielding. They use only the microstrip lines, or they use the CPV and no shielding, but this is maybe only for the demo boards. It is rather hard to find what is inside commercially available radars.
Okay, let me one more question. So if you can please show the S parameters.
This one?
Yes, for example, this one. Is it simulated or real measured data?
This is only the simulated data because we don't have it. Well, the PCB is with the antennas themselves and with the ICs, and we didn't have time and equipment to measure all of these lines on the PCB.
Last one question from me. Did you try to optimize your sizes of your topology to make it possible to produce in Russian companies, in available companies for you?
The thing is that there are certain requirements for the spacing between the wires, because it should be less as possible, because we don't want to have the coupling on the PCB, and we don't have the waves coming out from the lines on the PCB. And as this is the short-range radar and the long-range radar, and we do have only two ICs in this PCB line, then the feeding lines, they are rather long, and this is why we wanted to use the CPV line, and they are spaced just there is no more place when we can move it on the PCB.
Thank you very much. Thank you. Victor,
Thank you.
Applause, please. I think very interesting work. and very interesting speech. And now we're going to listen Nikita Sevostyanov from Novosibirsk State Technical University. Resonant controllers design for frequency-selective impedance-controlled DC microgrid. Please.
Okay. Hello everyone. I hope you are doing well and enjoy the conference. My name is Nikita Sevostyanov. I'm a first-year PhD student of Novosibirsk State Technical University, and today I'm going to tell you about our research on control system design for distributed spacecraft power systems. And I will speak according to the following outline, and firstly about the relevance of the research. Space industry is growing now, and you have likely noticed high attention to space today. Some people even talk about the new space race, and they attribute it to the following reasons. Firstly, that many countries seek to be part of space, to be independent and safe. And secondly, space is becoming commercial. Many commercial applications have appeared, for example, global internet, delivering cargo and humans to and from space stations, environmental monitoring, telecommunication and space tourism, and so on. And it makes space industry very attractive for engineers and scientists, and our research is related to investigation of spacecraft power systems. And what place does the power system have in spacecraft? Well, the power system is intended to provide onboard systems with electricity. The power systems must be as efficient as possible to be light and small, and the power systems must be very reliable and fault tolerant, because of no power system, no spacecraft. And these points lead to the statement that the spacecraft power systems are really worth to be investigated. A couple of words about the conceptual framework. This is a conventional spacecraft power system. There is energy sources on the left side, onboard systems on the right side, and special interface power converters to connect them. And we focused on the sources side power converters that are designed as one big power model with communication between the converters. And this is very outdated structure. There is another modern structure, modular system, where each power converter is designed as independent power model. For example, such models are being developed in NASA and produced by various space manufacturers. And we considered a new cutting-edge structure. Let me introduce it by two steps. The first step is removing the communications between the power modules, and the second step, splitting the board into several subboards. And this structure was named as distributed power systems or space microgrids. So there is a big main advantage of such systems over the modular systems, and it is inherent fault tolerant. For example, distributed space power systems resist power module failures and even board failures better than modular systems. So it was a background. So some words about the problems, the main problem and purpose. We stated the scientific problems as a problem of control system design for distributed spacecraft power systems, and stated the topic and the purpose according to this problem, and how developed is this topic today. The term space microgrid was introduced by scientists from Aalborg University in Denmark 2 years ago, but this topic is quite young and still not developed well. So the main problem of such systems is connected with the equal loading of power converters or equal current sharing. There are two approaches to build control systems such with passive current sharing and active current sharing, and we can compare them by power quality, presence or absence communication, and fault tolerance. And we took passive control methods as a basis and decided to improve power quality. The first result we obtain is the frequency-selective impedance control to improve voltage, steady-state voltage quality. The second result is Drude-based frequency-selective impedance control to improve steady-state current sharing. And the third result is flat impedance control to improve dynamic voltage quality and current sharing. And we developed an experimental bench to verify all these results. So about our partners, the largest satellite producer in Russia, Resonant company, is the main one interested, and the key points of the research were discussed in this company when I was in internship there 2 months ago, and the company is very interested in this research. So as a conclusion, I'd like to enumerate the main contributions, the main scientific contributions. We considered the most reliable and fault-tolerant structure of space-core power system, distributed power system, developed 3 new control algorithms for it, and verified the results by the experiments. And so that's all. And it was my pleasure to participate in the conference and this competition too. Thank you so much.
Thank you. Thank you very much. It was a nice speech. Questions, please? Please. Alexei, please.
So, yeah, thank you. So we see that you have really strong partners, but what is exactly your contribution in this work? So we see 3 or 4 different, scheme of control systems, and you show the difference, but what exactly? My first question, what exactly was your contribution? And the second question, you show the picture. So the first one probably was some simulation of this control system, and the second is like some results. So, is it like results, exact results which you measure by measuring equipment?
Yes.
Or okay.
Okay.
What about the first question? My first question.
Okay. You mean my own contribution in this research? Of course, I did this research with my scientific advisor, but I proposed these 3 control algorithms, and I developed the experimental bench to verify the algorithms. Well, it's my own contribution.
Okay, and what is it, your algorithm? how many line of source code you write, how many structure do you make, what is it?
Okay, I think that how many codes I wrote, it's not so important for
No,
this.
but you write it, yes? Okay.
Yes, of
Yes,
course.
okay, and you show free structure, no distributed, no how to say, it's enough simple. And what we usually in DC-DC converter, output transistor burn. And what control?
Well, I tried to highlight the main points of my research without in-depth details. If you are interested, you can read my articles, my papers. Well, that's all.
One question from me and from Konstantin, okay? Tell us, please, what Roscosmos interested in this project exactly?
What exactly from this research is interested
by Roscosmos company?
Yes, well, I input Roscosmos here because Resonant company is a part of Roscosmos.
I see.
Yes, and the main direction in spacecraft power systems and of course in Resonant company is to make them distributed or modular without and more reliable and fault tolerant. And I tried to make my algorithms without communication between the power modules because it's difficult for them to make it based on Russian components with high speed communication.
Thank you. Konstantin, please.
So I have a small question. Because this is for spacecraft where the critical is the weight. How much change your idea, your code changed the weight? Smart.
Okay, it wasn't measured the change of weight or volume of spacecraft or spacecraft power system because it's difficult to implement new technologies, new innovations in space industry.
Your estimation.
Quickly.
Just imagine that everything is possible.
My own estimation.
Yes, of course.
Well, I noticed the project of NASA. Just a second. This project AMPS, and they measured the change of weight and volumes of their spacecraft power systems when they implemented modular power systems, and they estimated it around 20% reducing.
Okay, that's great.
Thank you very much, Nikita.
Thank you.
Sorry.
Around 2010, there was an increasing demand for 4G networks.
I had some big concerns regarding LTE. Vodafone Germany is operating 4 networks. Unfortunately, the worst case would be to add now with LTE network number 5, LTE 800 and network number 6, LTE 2.6.
当时是我们和客户讨论，觉得原来传统的建网方式的话都是重复建设，所以成本也很高，维护也很复杂。
So we talked with our customers again to see if we could combine 2G, 3G, and 4G network equipment into a single unit. That's when Single RAN was developed. According to our customers, this was a very attractive technological invention.
Our vision is giving all of our customers 2 years from now broadband data coverage where we do have voice coverage today. That means countrywide.
In 2010, the 4G LTE 800 MHz commercial service was first launched in Germany. The 800 MHz spectrum is best suited for the vast countrysides of Europe.
In these so-called white spots, outside, in the countryside, in the small villages of Germany, hey, now it's really fast internet in my hands.
And now our next finalist, Mikhail Pozdnyakov, and simulation of a sensitive element of a MEMS-based pressure sensor operating on the thermal detection principle.
Good evening, colleagues. My name is Mikhail Pozdnyakov, and I am a graduated student from National Research University of Electronic Technology. And the topic of my speech today is simulation of a sensitive element of a MEMS-based pressure sensor operating on the thermal detection principle. In the modern world, MEMS pressure sensors are used in variety branches of science and technology. For example, is manned aircraft and airborne equipment, mechanical engineering, medicine, and chemical industry. Currently, there are many sensors, the main of which are capacitive, electromagnetic, piezoelectric, optical, and resonant type. Despite the fact each of sensor has its own advantages, what you can see on the slide. However, there are also a number of disadvantages, such as narrow pressure range, mechanical and thermal instability of sensitive, and etc. In this regards, I propose a new principle of detection pressure. It is thermal detection principle, operating in a wide range of subatmospheric pressure. The sensor design consists of a metal deformable membrane and a fixed dielectric membrane in the cavity of the gas with low thermal conductivity. After the upper diaphragm deform under the influence of pressure drop, which leads a heat outflow, change of thermal resistance, and temperature of the heater. This change is quite sensitive of small deformation of the heat conducting membrane. The proposed concept has these advantages. It's high resistance to temperature, vibration resistance, high sensitivity in subatmospheric pressure range, and the last, low power consumption. The main tasks is selection of the optimal sensor design to obtain the maximum sensitivity, selection of the material of the membrane to ensure its sufficient mechanical strength and thermal conductivity, and the last, selection of the optimal gas medium inside the cavity of the sensitive element of the pressure of the sensor. The COMSOL multiphysics CAD used to design the structure and simulation the physics process to work. On the current slide, you can see the design built in this program, and some simulation parameter used in modeling. However, in microelectronic devices with very small dimension, when relay number, what you see in the slide, less than 1,700, the problem of membrane deformation and thermal problem can be considered independently. And the first result of my speech is membrane deformation with pressure drop. On this slide, you can see the left graph of the modeling of a membrane under excessive pressure. The sensor can be used the same way as altimeter. What is the membrane will bend outward. The next step, it's right graph, analyze the deviation in both direction to study the behavior of the membrane. As can you see from the graph, membrane has same displacement pattern in both direction. The next step is simulation heater temperature. As function of external pressure for three different gases, which graph you can see on the slide, it's left. Different temperatures are associated with different temporal conductivity of gases. The right graph shows the temperature increment as a function of pressure drop. The final and most important functional dependence is sensitivity of the sensor to pressure drop. Both graphs are presented in logarithmic form. As can you see from bottom graph, the sensitivity change slightly in the range close to atmospheric and monotonely decreased with increasing pressure. Operating pressure range is from 10 to 100 millikelvin kilopascal. The maximum sensitivity is 25 millikelvin on Pascal for xenon in work gases. And last, you can see a visual representation of some steps of fabrication process flow was carried in the Tikhat-Silvaco system. The simulation of the fabrication process flow was carried out in order to assess the possibility of manufacturing a thermal pressure sensor for this fabrication process flow. The final design membrane pressure sensor could be obtained by applying wafer bonding technology. On the slide you can this route for one substrate and final is bonding structure. At the moment, the first batch of the sensor has been manufactured according to the topology shown on slide for subsequent experimental measurement. And this development was also supported GaAs seal, where you can see the support letter and clipping from it on the slide. Thanks for your attention.
Thank you very much. I think it is very interesting work. Question, please.
Please stand up.
Thank you. So you showed the first table, but such table has no models, prices, even manufacturers. So it's just different techniques. And why did you choose a MEMS sensor? I mean, it also has some disadvantages. And you didn't tell the reason why you choose a MEMS sensor.
Where membrane pressure sensor have a higher sensitivity at relatively small sizes. Final structure is 1 millimeter or less. What you see in the table, it's experimental number from sources what you can see in right column.
I mean, sometimes the techniques or the techniques what is used for manufacture some sensors, it doesn't matter. Sometimes the price it's much more important, or accuracy, or another parameters. So I think that's is non-objective analysis. And structure of your sensor, it has gas inside. So
yes.
Yeah, how does this gas? how do you build such sensor? I didn't understand. So how gas go into this sensor? How this is? Yeah.
The final structure built with free substrate. We have a central instrument substrate.
So it's given by heater of some area of sensor.
Repeat please.
Is gas based on heater of some areas? I mean, you just put something inside of area and then heat, and then gas go out of some
The
materials. Okay.
Sorry. I don't know how say this. Sorry.
Okay. One more question. You simulate and where is
I can say
first of all model of it and what do you do? Write program or use commercial software and so on. What do you do? And where is measurement of your device and how compare it with simulation? Is it okay or not okay? What is the model?
I'm saying it went. First batch sensor has been manufactured, but it not have experimental measurement because it's the moment.
You can answer to Alexei in Russian, and
Yes,
we will
of course.
translate. Please.
Can you repeat in Russian, please? Чтобы я понял.
Как газ внутри получается? В процессе чего? Каким образом он оказывается в этой прослойке?
В целом общая конструкция датчика состоит из трех.
In English.
Very short Russian answer, and I will translate. Okay?
Окей. Три подложки. В одной подложке расположен сам чувствительный элемент. И во время сборки всего этого дела вакуумируется центральная газовая камера.
Okay. 3 substrates. Okay. Stop speaking in Russian, please. It was the exclusion for the Mikhail. Okay? Only for the Mikhail, because it was very interesting work. Alexei, it's okay? It's enough. Thank you, Mikhail, very much.
Thank you.
We have one question.
Please.
Yes, please.
This is Konstantin. I'm also from MIET. Several years ago. So my question is, what you can say about reliability of this device? How long it can serve?
I think this device is need to correct sometimes, and cause gas in the chamber can.
Okay, I see. And comparing to other such similar sensor, are they also use some gas inside this structure?
Yes, we can use another gas in.
No. I mean, your competitors who develop the similar structure, maybe, do they also use the gas inside?
No, with know-how concept and another research on this work does not exist.
Okay, thanks. That is the answer on my next questions. Thank you.
Thank you.
Thank you very much. Now we're going to listen Valeriy Barmin from Institute of High Current Electronics. radiation of radio pulses excited in a non-linear transmission line with periodically arranged diodes based on GaAs structures.
Hello, my name is Valeriy Barmin, and today I am present about instead of my colleagues Arman Khajibekov. Let's start. My mistake. My first job called radiation of radio pulses excited in a nonlinear transmission line with periodically arranged diodes based on gallium arsenicum. The development of means for generating electromagnetic pulses is an actual and promising task. Sources of short EMP with sub-nanosecond fronts used in powerful electromagnetic emitters and other requirements. Semiconductor diode can serve as key elements for sharpening sub-nanosecond front. For example, gallium arsenicum as diode allows sharpening the pulse from 300 picosecond to 1.5 nanosecond and voltage of 700 voltage. The development of an installation for the emission of pulses excited in a nonlinear transmission line with periodically located diodes based on gallium arsenicum structure. And the measurement of the level of the received radiation is actual task. To simulate on nonlinear transmission line in CST Microwave Studio, a coaxial line with a corrugated center condition with a resistance of 10 ohms was shown. Figure 2.8. In this model, when half the pulse amplitude is reached, the conductivity of the diode change linearly from 1 Siemens per meter to 1 mega Siemens per meter in 200 picosecond. This is from initial pulse. In this case, the maximum output value of the amplitude of high frequency oscillation at a frequency of about 1 GHz is about 30% of amplitude of the initial pulse. This is blue curve, and considering the limited capacitance of diode of 30 picofarads, the amplitude is 20%, is right curve, free. The generator of high frequency oscillation in a nonlinear transmission line can be explained by the synchronicity on the velocity of the shock wave and the phase velocity of oscillation at the excitation frequency. Next, of the slide you can see the appearance of the electromagnetic pulses generator and consists one and accelerator sinus 160 and two coaxial lane and three nonlinear transmission line into coaxial line. And the manufacturing nonlinear line is similar to the simulate on 3B. Next, in the out experiment there were 7 diodes, and in figure 8 which were installed in series in the corrugated condition section. The remaining free section were short circuit which jumps. The measured voltage level before and after the nonlinear line when operating into 10 ohms. Matched load shown in figure B. And dash before and after nonlinear line. The generated oscillation frequency is order of 0.85 GHz. The emitter was a conical helicate antenna, figure 5.8, and with a characteristic radiation polarization close to circular and a wide frequency range. It is calculated using antenna theory and CST optimization. A cone transformer which a characteristic impedance from 12.7 ohms to 19.5 ohms in install an antenna output in a carousel waveguide. Next, alright. This slide just shows the calculated frequency depends of the reflection coefficient S11 of the antenna at a frequency of 0.8 to 0.89 GHz. The value S11 is about negative 20 decibel. And BCD and photos the manufacturer antenna. Measurement stop. They measure the emission of the excitation radio pulse in an open space. The circuit shown in figure 7. The distance from the transmitting to receiving antenna was 2.2 meters. The receiving antenna is a half-life vibration with effective absorption area of 50 millimeters per 2. The measurement of the voltage waveform from the receiving antenna was performed on the oscilloscope with 6 GHz bandwidth. Okay. Next, conclusion. In conclusion, a device for generating radio pulses was developed and manufactured on the based on linear transmission line with periodically located gallium arsenicum diodes, which has small dimension, high frequency and amplitude for generation oscillation. The effective potential of the system of 2.1 kilovolts has been reached with the radiation of radio pulses from the set.
Thank you.
Thank you.
Okay. Please, questions for Valeriy.
Please stand up.
Yeah, okay, thank you. So, as I understand, your work is devoted not to only simulation, but also to experiment measurements. Yeah, and what method did you use to obtain your diodes, or you just took already existed diodes?
Obtain is diodes simulation in System Studio.
No, what? How did you grow your diodes, like in your to measure your experimental device, or you just bought it?
This is a special step in previous investigate this gallium arsenicum diodes and silicon diodes used.
So my question is, you did not say nothing about a preparation of your device. How did you build it? Or maybe I missed it. Can you tell something about it?
I'm not understood. Please repeat.
Okay.
Simple
Well,
question.
okay. I have another question. So you showed us a lot of figures, a lot of graphs. Can you simplify it for me? What is the main characteristics for your device, which you obtained from these results, from these figures? Because for me, it didn't tell anything.
Figure 5?
You have enough graphs, like enough dependence of, I think it's voltage through time or through length. So what is the main properties which you obtain from it? What's the main characteristic of your...
The main result of your work.
Yeah.
In English, please. In English, please.
Thank you, Russian speech. This generator and clear silence investigated from creating compact megawatts RF generator and future and increase pulse power generating.
Okay, I can.
And increase lifetime.
What is your main graph? This one? Which you obtained?
Yeah.
Yeah, and what information I can get from this graph about your device?
I think this discussion will have some problems, right? Okay, show us the main plot of your work.
Excuse me, Russian language. То есть, как это работает или что?
No. Okay.
Результат работы?
Everyone who interested. Okay, Roman Горбунов, please.
Let me help to clarify previous questions. So we try to understand what is the main result of your work. Is the device, is it an idea to build this device, or is it simulation? What it is? Is it?
This my parts investigation and physics and semiconductor and EMP generator.
Generator. So you build generator. You have built it.
You have built it.
Can you show it or list the main characteristics which you possess as advantages of your device?
Yeah.
Please.
Okay. Yes. Everyone who want to understand the Valeriy's work, please take some time with the Valeriy with coffee or tea and discuss all its results. Thank you very much. Thank you. Development of infrared scene model in a wide wavelength range.
Good evening, everyone. First of all,
speak in the microphone.
Let's start. Machine vision systems are among the most significant robotic applications, and in order to achieve the highest performance of such systems, they require the next photodetector characteristics.
A widest possible input dynamic range allows the signal latency and an ability to work in several wavelengths, especially in infrared, because there are some robotic applications that is heavy and often dangerous for a human being. One of the most effective way to achieve the first two characteristics is to use a different readout technique, also known as dynamic vision sensor. In this readout technique, the sensor photodetector outputs a stream of asynchronous events, which contains no data, only the information about that on this pixel an incident radiation is changed by a threshold. This helps us to greatly increase the input dynamic range and decrease the number of not important information as we can get from frame-by-frame architecture with static images. Another way to increase the effectiveness of photodetectors is to use spatial differentiation as implemented in our eyes. The signal coming from an eye to a brain is a function of incident radiation difference between a central part of some retina area and the peripheral. This results in a very high input dynamic range, but is often a reason of some visual illusions associated with spatial differentiations. So we proposed a model of photodetector with such techniques presented before, and the signal and the output of such sensor will be an asynchronous event stream. And fortunately, we have a neural networks class that is inherently asynchronous and works with simple events called spikes. And this neural networks is also known as spiking neural networks. So we have a system that will interpret this kind of data. Now we want to we found out that machine vision systems require new kind of sensors, and we want to make such sensor through a thorough study, research, and several model experiments. But if you want to implement a visual sensor, we just use any of those visible sensor, visible engine simulators, create some input data and get the results. But in our case, we are developing infrared sensor, and there is no infrared scene simulators available now. Unfortunately, we cannot use video information from existing infrared photodetectors because they already contain the limitations imposed by the architecture. So we need to develop some software tool that allows us to make some input data. And I'm showing you the results of my work. An infrared scene model. This software toolkit consists of three parts: the scene, an engine, and a window. A window showing us the results of a rendering of the infrared scene. The scene consists of several objects where each object can has its own material, such aluminum glass, etc., has its own temperature distribution and position in the world space. The scene also contains the environment model and optics. They impose the limitations on the input photodetector signal, which is modeled by camera class, which may be visible and infrared. And the engine is a novel visualizer of infrared scenes in a wide wavelength range based on Vulkan API. It uses several graphics processing units to simulate the infrared scene. Infrared simulation process consists of several steps. First of all, we upload our 3D scene to a graphical processing unit. The scene may be created by any conventional tools for 3D modeling, such as Blender, Autodesk, Maya, and so on. Then we choose models for our system. Models for atmosphere, optical system, photodetector, and so on. After that, we set the wavelength of interest, wavelength range of interest, and starting simulation. After simulation result are presented as several wavelength point images. We then sum them up and get the resulting incident intensity on focal plane of photodetector. In detail, the same rendering graphical pipeline consists of the next steps. We upload data and then proceeded with vertex shader, which places the objects in the world space. And if we want to look at the realistic image, we just pass the data to the fragment shader and get the realistic images of the scene. But if we want to look at the infrared scene, we estimate the spectral radiance of given bodies, multiply by their grayness values based on material, apply atmosphere and optical system responses, and get several points in infrared scene. On this slide, I show the results of several wavelength points of airplane F-16, which has some temperatures of engine, near engine body, and the temperature of the body. Then we sum the points together and get the resulting image on the photodetector. So we can use this scene simulator to simulate any kind of photodetector model. Thanks for attention.
Thank you very much. Okay, question, please.
We have one question.
Thank you for your presentation. My name is Yaroslav from Huawei. So the question is, how do you verify that synthesized images are close to real? So how do you verify that simulated results are correct?
To be honest, I haven't did this job to verify how the real images are correct for to the results of my simulation, because real images contains much more effects that I haven't included in my model for now. For example, inter-objects, radiation interaction, and so on.
So is it kind of future plan?
Yes, it's a future plan.
Okay, thank you.
Thank you. More questions? Please, please. No, please, for expert first.
He was first. Okay.
Thanks. Branislav, научное оборудование. As far as I can understand, you already have a customer for this project, or not?
I have no customer for this project. This is our innovative project with my scientific advisor.
Okay, but the idea, you've got it from maybe industries that need simulation for testing their products, yeah?
Yes, I am one of the developers of neuromorphic chip Altai, Motif and they are inherently spiking neural networks hardware simulator, little chips. And as when we have developed it, we find out that there is no sensors that have output data that would be inherent kind of input information for such chip. This simulator is a framework for creating some high-speed photodetector sensors in order to create some compact autonomous devices using our chip.
Okay, thanks.
Thank you. And one more question, please.
Please stand up.
Okay, on the last slide you show us 4 different pictures of airplane. Can you explain me why you chose so close wavelength? Can you expand it to choose not 2, 5, 8, and 13, but like 2 and 100, maybe the result will be different and we can see more.
Yes. I choose those points of wavelengths because many modern infrared photodetectors are working in the wavelengths of from 2 to 13 micrometers, because there is a windows of atmospheric transparency. In these wavelengths we can see through atmosphere. This is one of the most important tasks for infrared technique. If we are interested in any other wavelength range, we can choose it because the Planck equation has no limits to wavelengths.
So as I understand, your approach can be expanded to other wavelengths.
Yes, you're
okay.
right.
Okay, and one last question from Alexey Zhdanov, please.
Thank you. As I understand, your software and hardware solution, it's like infrared camera, like advanced infrared camera. Is it possible to use medical purposes, especially for analyze temperature fields, even for some? Some producer made it calls incubator for neonatal purposes for small babies, and during treatment, medical device have to analyze temperature area. So is it possible to use such a system for medical purposes?
This system is not a model of infrared photodetector. Infrared photodetector is a resulting device using such system. Such system is a simulator of various infrared scenes. We can create it and look at them in very wide range of wavelengths, materials, temperatures, and so on. We can create input data for analyzing such sensors, and the sensors may be used in every appliance that human can create.
So it means we may use any sensors, it's just up to software, up to your purposes.
It's just a software simulator for testing and approbation some infrared photodetectors. For example, on this slide I just showed the special differentiation technique on infrared sensor. It's the same picture, like picture, but the only edges are resulting images.
So your scientific work only apply neural network for your simulation? Yes? No?
No.
No.
My scientific work is to create a new kind of photodetector, which
no photodetector. Why do you have experimental piece of photodetector?
This kind of photodetectors is not existing now.
Why do you think your model will be the same like?
This is the reason why we need to model it, because if we model, we won't get the results. Is it effective or not?
Okay. Thank you very much, Dmitry.
Thank you.
We have 2 works more, okay? Let's move on. Nikita Lysenko with area selective MOS-CVD synthesis of what to be and what to me phases on a silicium substrate. Please.
Hello, dear colleague. Let's start. Vanadium dioxide is material considered as material for post-silicon electronics due to its unique properties. Vanadium dioxide is polymorphic material, and each phase has own optical and electrical properties and synthesis condition. The most interesting for practical application phases are B and M phases. properties such phases shown in the table. Heterostructure based on different phases of vanadium dioxide is a practical interest, but formation such structures is a big challenge. However, there are still no publication works devoted to solving to formation such structures. The main problem for structures, heterostructures based on different phases is that each phase has own special synthesis condition. For example, B and M phases. B phase has temperature of synthesis is lower than M phases. Therefore, the most CVD synthesis, simultaneous most CVD synthesis in one process and one substrate seemed impossible. Such phases of dioxide vanadium. The work devoted to solving this problem. Let's move on experimental details. Substrates, silicon substrates and silicon dioxide substrates were covered by PVA. It is polyvinyl alcohol, and polyvinyl alcohol. Some substrates were covered partially. Synthesis conditions were established necessary for synthesis of M phases. The study by SIM and X-ray diffraction and resistance measurement at different temperatures. As a result of this study, we found effect of PVA layer thickness on the main characteristics of vanadium dioxide films. The main characteristics is the main characteristic are morphology and resistance ratio under resistance between resistance under normal condition and resistance under heating. The main characteristics change from typical for M phases to typical for B phase. Study by X-ray diffraction confirmed this. Thus, we have shown the possibility controlling phase composition on vanadium dioxide films by a preliminary coating without changing synthesis condition. On substrates with partially coating, we found that where PVA layer was, the B phase grew, and where PVA layer was not, M phase grew. Thus, for the first time, we experimentally obtained area selective B and M phases, one substrate, and in one growth process. Conclusion. Such structures can be useful for formation a new device and integrate circuits based on vanadium oxides and its heterojection and by technology full compatible with standard silicon technology. Thank you for attention.
Thank you, Nikita. It was a perfect timing. Thank you. Questions, please? Questions? Okay, I have a question. Tell me, please, as for person that is rather far away from your research topic, what the most possible and most significant practical application of results of your work?
It is it is formation sensors with high accuracy. Sensor gas sensor and temperature sensors. It is all based on oxide of metal without silicon.
Okay, I see. I think it is very useful for a lot of area.
For future.
Yes. Yes. Another questions, please. Please.
Maybe we understand nothing, but how do you think? Is it possible to use your sensor for artifactal noise?
It is no sensor. It is the possibility for forming.
Why do you think that it's possible to use it like sensor? And for what is it?
In the future, it is maybe okay.
Okay. Oh, please.
Sorry, maybe I missed. Did you already get some practical results on practical technical?
Practical results, or
it
is the practical results.
So this was done in your laboratory.
Results of studying the possibility forming such structures.
So you just get it from some literature and something like that. Oh, okay, thank you.
Thank you very much, Nikita. Okay, and of course, Vitaly Tumashev, a new technique of aurum nanopattern formation for metal-assisted chemical etching of silicon.
Hello everyone, I'm glad to present my research work.
Microphone,
a new technique of gold nanopattern formation for metal-assisted chemical etching of silicon. In recent years, semiconductor nanostructures with high aspect ratio, such as nanowires or nanopillars, have more of great interest. Due to the unique electric, optical, thermal properties, they are used to create solar cells, vertical transistors, gas sensors, etc. It is important to emphasize that exactly highly ordered array are needed for a number of applications, such as photonic crystals or integrated circuits. Thus, a simple technique is required to fabricate such structures over a large area. The method of metal-assisted chemical etching, so-called MACE method, allows one to obtain structures with aspect ratio greater 160 to 1, smooth walls, and this method doesn't require special conditions such as a vacuum or atmosphere dangerous gases. The essence of this method consists in the local dissolution of silicon substrate only under a thin metal catalyst layer. The key stage and problem of MACE method is the formation of metal nanopattern over a large area while maintaining the purity of silicon substrate only under the metal layer. In our work, we have developed non-transfer printing method for MACE method. Non-transfer printing method, this method allows one to obtain metal pattern over a large area with nanometer resolution on almost any substrate. The essence of this method is shown on the slide. Gold or metal, a thin metal layer, is deposited on nanostructured stem surface. Then the transfer metal from stem surface to substrate surface occurs the mechanical contact. In our work, we used this method twice to form gold nanogrid on silicon wafer. But until now, no one has applied this non-transfer printing method for metal-assisted chemical etching because there are significant problem of creating a clean semiconductor surface under the metal layer. But in our work, we managed to solve this problem by using additional water-soluble layer of polyacrylic acid and new method of removing it in water vapor while rotating the sample on centrifuge. We found the optimal conditions which made it possible to completely remove polyacrylic acid and form perfect gold nanogrid on silicon substrate. In this same image, you can see gold nanogrid on silicon substrate. At the final stage, the operation of metal-assisted chemical etching were performed. As the reaction goes on, this nanogrid sinking down, forming arrays of silicon nanowires with square cross-section corresponding with geometry of gold nanopattern. In this image, you can see final structures, arrays of silicon nanowires. Also, this method allows one to obtain and more complex structures. For example, in this same image, you can see superperiodic gold nanogrid, and using this nanogrid, we obtain an array of nanopillars with various cross-section geometry, and the minimum nanopattern diameter is 10 nanometers. These structures can find application in optic, for example, plasmonic nanomaterials or plasmonic metasurface and metamaterials, and etc. Thus, a method of formation metal pattern over a large area for MACE method is proposed. Gold nanogrid on the surface of 3 each silicon wafer and ordered array of silicon nanowires were created. Superperiodic gold nanogrids were fabricated, and silicon substrate were created from arrays of nanopillars of various cross-section geometry. And the originality and simplicity of this method make it possible to create technology for mass formation of high aspect ratio nanostructures on semiconductor surface with large area more than 150 centimeters square. Thank you for your attention.
Thank you very much. Any questions, please? Please.
Yeah, thank you. So, as I understand, your novel, this technique is novel, and you proposed it like first time. And as I see, it's for me it's pretty similar for like plasma etching technique. And can you tell the difference between your technique and plasma etching? Because we, as we say, okay, because we know that the high of etched substrate, like you said that it can reach like 100 nanometers. It strongly depends on diffusion line and so on, and how your technique compared with, for example, plasma etching, and what parameters in your technique are crucial for etching.
Thanks for your question. If you correct your question, yes, reactive ion etching used for performed for create these structures, but this method our method allows obtain structures aspect ratio more than 116, and is without without damage of this gold nanopattern. I think this layer 25 nanometers, but if we use reactive ion etching, we destroy this nanostructures.
Okay, thank you. One more question.
Can you print only periodic structure or arbitrary structure?
No, we can.
No, question is, you receive 10 nanometers resolution.
Yes.
It's very, very good. And can you, for example, make silicon chip after that? Is it possible to implement it or not possible? How do you think?
I think it's possible.
When? Is it more cheap and so on? No, you see now, now fabric produce 7 nanometers resolution. In future, maybe 1 nanometer. Can your approach do it? No, maybe in future. How do you think?
The goal with structures, geometry of with nanowire.
Only periodically,
very highly ordered massive. Yes, periodic.
Only periodic.
Yes. We can use another stamp, and we obtain another nanostructures.
Please, Konstantin.
In continuation of the question, so you should use stamp.
Yes.
But this stamp also has small.
Yes, with
size.
stamp we obtain.
How to create this stamp?
Yes, with stamp we obtain electron lithography. But only one step. Only this step. Only one. This stamp, but this stamp use more 1,000 times in future.
Okay, and whether this technology is applicable to ASIC production? Somehow, I'm not sure. ASIC, just application, integrated circuits to produce integrated circuits.
Yes, there are articles where obtain vertical transition, for example.
So in future, nearest future, we can do the same. Yes. So, and another question. So you seems to me that you have already produced such nanostructures and have real. This one, is it photo from your work or from some?
Yes, it's in our work. Yes. We obtain only this massive, but we need, for example, crossbar structure.
Okay, thank you. Thank you very much.
Thank you very much, Vitaly. Nice work. Thank you. Okay, that's all our finalists. Thank you everybody for your attention. It's our first experience in such activity. I think you like it. We appreciate any feedback from experts, from finalists, from listeners about our work. Please don't hesitate to contact us. And all of participants, all of finalists now get the certificate of participation and some brochure from my journal. Maybe you want to publicate in this journal. I should do this. Thank you, everybody, and good night. And about winners, yes. Now we check all the expert assessments list, and tomorrow on the closing ceremony, right, Roman, we will announce the winner. Okay. Certificates now and the winners tomorrow.
What sparks innovation? Is it thinking bigger or smaller? Does it strike fast or slow? Is it a flight of fancy or a stroke of genius? Innovation is everywhere, on desktops, in pockets, on wrists, in us. Innovation answers big questions, finds inspiration anywhere. It connects great minds, imagines the impossible, and propels us forward. At Keysight, innovation inspires us, fuels us to redefine precision in measurement, to surface insights, to remove barriers so the next stroke of genius is yours. We are Keysight. We accelerate innovation.